Welcome back to part 2 of our single-cell RNA-seq analysis tutorial using Surat. In part 1, we covered the creation of the Surat object, calculated key quality control metrics, and visualized them using violin plots. So the violin plot that has been generated, you can see here in my screen. Yes, so this was the violin plot that was generated yesterday. And we have compared three quality control metrics. That is the number of feature RNA, that is the number of genes that is expressed, the number of RNA molecules in count. It is counted by counting the UMIs or the unique molecular identifier, which all I have explained in my previous videos. And also we have generated the percentage of mitochondrial gene expression. So each point is a cell. The violin plot has been explained to you in the previous video. The violin plot helps us to assess the number of genes, total RNA counts, and mitochondrial gene expression, as already said. I've explained how to interpret those violin plots in a very short video. You'll find the link in the description box below or in the YouTube cards above. Now, let's continue with our quality control visualization using scatter plots. To dig deeper into quality control, we are going to plot scatter plots to identify potential outliers that might have escaped in earlier filters. I'll just I'll reduce the size of this plot. So you can also see the environment that we have loaded our data, pvmc.data, and we have created a Surat object named pvmc. This is the code for generating the feature scatter plot. If we run this, I'm increasing the size of the plot so that it is visible. If you look at these plots helps us spot correlations and anomalies. The first plot shows N count RNA versus percent mitochondrial gene expression. So what happens here is it helps us to identify the cells with high RNA content and high mitochondrial gene expression. So if there's high mitochondrial gene expression, there's a possibility that the cells are either dead or stressed. The second plot shows nRNA count, or the number of UMI molecules versus UMI molecules are nothing but the number of RNA molecules present in the cell versus the gene. Features are nothing but gene. And it reveals the relationship between RNA count and the gene diversity. Ideally, they should be roughly linear relationship. Cells far off this diagonal relationship might be multiplets or emptied out droplets. So we can filter out those cells. And if you visualize, yes, we are getting a diagonal relationship. And the cells which are very far away, as you can see on the top two cells, they can be outliers. And even in the first plot, the top two cells, so we are getting a pattern over here. We can filter out such cells. So these graphs are very useful. Okay, together these scatter plots are together these scatter plots are of great importance to check or to confirm that our filtering thresholds make sense and that we have cleaned our data appropriately. Now, the values that are above these scatter plots represent the Pearson correlation coefficient R between the two variables that are plotted in the respective plots. In the first plot, the value of R is minus 0.13 for N count RNA versus percentage mitochondrial expression of the genes, which indicates a very weak negative correlation and suggesting that no strong relationship between total RNA count and mitochondrial gene expression. This is expected unless there are stressed or dying cells. So, in short, we can say the quality of our data set is quite good. In the second plot, the value is 0.95 for N count RNA versus N features RNA, which shows a very strong positive correlation, meaning that higher RNA counts are closely linked to higher number of detected genes as expected in normal single cell RNA-seq data. This correlation is a good sign that the data behaves appropriately, and any deviations could point to potential technical issues such as doublets. Now, moving on further, we will filter the data set based on specific criteria. Then we will perform normalization, find variable features, scale the data, perform dimensionality reduction, and explore clustering. I have discussed all these topics in the another module course, that is AI ML learning course, where I have discussed about normalization. What are the variable features, what is scaling, and what is performing dimensionality reduction. So that is a total different course, and it is freely available in my Google Classroom. I'll give you a link down in the description box over here. But for now, let us start filtering the data set to remove these cells that don't meet our quality control threshold. So this is the code. We are subsetting our data set, and first we will run this one. So yeah, subsetting has been performed. Now here actually we are applying the filters to retain only those cells with between 200 to 2500 genes. So this is the range that we are giving, that a cell should at least have 200 genes and not more than 2500 genes, and less than 5% mitochondrial gene content. So MT is less than 5 represent less than 5% of the mitochondrial gene content. Now, this is a common practice in single cell RNA-seq analysis to remove low quality cells. Moving on further, we proceed with normalization of the data. Normalization is essential in single cell RNA-seq to adjust for differences in sequencing depth between the cells. Some cells would have sequenced very deeply, and we have a large number of counts or the RNA molecules. So those molecules may bias the output, and they'll mask the data, showing a high expression level. Whereas in reality, it would be just the higher duplication effect. So that's not actually the expression, but also it should not be the expression level, but it should be the number of copied RNA molecules. So our data should not be biased. So we normalize these counts, and here we are using the log normalize method. As you can see in the code, it's clearly mentioned the method is log normalize, and the scaling factor is of 10,000 by taking, and then with help of these attributes, we'll perform the log transformation. So when I run this code, here normalization has been performed. Now we move for feature selection, where we'll be finding the variable features. We will be identifying the 2000 most variable genes across the cells, and we'll be using a VST method. These genes are the ones that show the most variability across the cells and are useful for downstream analysis like clustering. We then create a plot of variable features with the top 10 genes labeled for easier visualization. The VST is also called variant stabilizing transformation, and it is commonly used in single cell RNA sequencing data analysis to normalize and stabilize the variance of gene expression data across different expression levels. The primary goal of the VST is to transform count data into a form where the variance is less dependent on the mean, where the mean becomes zero, and which is important, much important, because in raw seq analysis data, highly expressed gene typically have higher variance than lowly expressed genes. So we want to balance that out, and that is why we are using this attribute. Now we are running this code, this one, the PVMC find variable gene features. This is a function, and the method is VST, and we have chosen the top 2000 variable genes. And you see here the action has been performed, and then we'll be identifying the 10 most highly variable genes. So we are putting that data into top 10, and we are only getting the variable features of PBMC of those 10 features, right? Because already it has been arranged as the most variable genes. So we are just getting the top 10 variable genes here. Okay, but if I run this code, so this action has been performed. And now to visualize that, we'll be plotting with the help of variable feature plot. That is a function where we can visualize the most variable genes. So if I run this variable feature plot, so all the 2000 variable features I can visualize. And in plot 2, we will be looking at top 10 variable genes, and we'll be locating them on the graph. And here, plot 1 plus plot 2 will give a grid of uh, two plots side by side. If I run this code, usually you need a very bigger canvas. Canvas is not big enough. I'll try to run it again. Yeah. So now you see we have generated our um, plot where we can visualize the most variable genes. So all the 2000 genes are plotted over here. How to interpret this? The black colored data are, so first of all, the x-axis is the expression level, and the y-axis shows the variances. So each point tells us the gene names. The black colored genes are the genes which does not help us in looking at any variability. And the genes that are red in color are those genes which are highly variable. And we had also, annotated and named the top 10 variable genes in the second plot in your right hand side, you can see. So here we can understand the variability between the genes, and we know which features we must select. So we have selected top 10 genes, and we know where they lie and what is the structure of the data. Next, we will scale the data. Now, this step is very crucial for the upcoming PCA analysis and other dimensionality reduction techniques because it will standardize the gene expression values. We are also regressing out the percentage of mitochondrial gene. We don't want it, okay, to interfere with our data. And it could be, as I've already told, that mitochondrial gene expression levels could be an indicative of a stressed or a dying cell. So let me adjust the window first. Scale it small. If you are running this plot and you don't get the visuals properly, please try to increase the size of the plot pane and run it again, like I did in the video, right? And you see in the environment section, we are getting all those things. So top 10 values also we have got, and we have also stored the different plots in our environment, right? Proceeding with the scaling, next step, Now we are creating all genes variable where we'll be adding the row names. Now row names will be nothing but the gene names which are stored in the PBMC Surat object. Then we will be giving a function scale data where according to all these gene features, so features will be the name of all the genes, and we'll also regress out the percentage mitochondrial gene expression that is not required for our data. And I have commented out this particular code. Now I want to tell you that these both performs the same function. So scale data is actually an older function that was used till Surat 4. Now Surat 5 has the another function that is SC transform, where uh, the format to write the syntax is slightly different, but nonetheless both the function allow us to use vars to regress, that is variables that we want to regress out. So right now for the sake of this demonstration I'm using the older version. You can use anything that you want. So when I'm running this, so first I had to run all.genes. So I'm running this, and you can see in my environment all.genes is stored here. And when I run the second code, I'm using the older version. When I'm just a second here. Okay, so when I'm running this, so it is regressing out the percentage of mitochondrial gene. Before moving further, I would like to clarify that regressing out mitochondrial gene expression helps remove the technical variations associated with poor quality or stress cells without losing potentially valuable biological data, and it allows us for a more accurate analysis. In contrast, removing mitochondrial gene expression entirely excludes these genes or cells from the dataset, which may discard relevant information. Regressing adjusts for the unwanted variability while preserving the data, making it a more effective method for addressing confounding effects in single cell RNA-seq analysis. So the operation has been performed. Regression has been done and scaling is also done. We have centered and scaled the data matrix. So in layman terms, scaling means the most of the value will be between 0 to 1. That's it. So that the numbers should not be very far apart. So the very high value number with a very high value will dominate your data set. And these are the basics of statistics that we must know, right? And moving on with the further analysis, we now perform principal component analysis, that is PCA, on our data using the variable features that we have just selected and scaled. PCA is a linear dimensionality reduction technique, and it reduces the dimensionality of the data and also preserves as much as variance as possible. We visualize the first few components and examine the loadings. Now it will tell us how each gene contributes to each component. So component will be the variability. For more details on PCA, I would like you to go through the video that I'll be linking in the description box below, or I'll put here in the video as a card. We also generate PCA plots and heat maps to visualize and inspect the clustering of the cells in further steps. Okay. So performing linear dimensionality reduction after scaling, obviously. So here the function is run PCA, and the features are the variable features that we have already selected in our object PBMC. Fine. So we have already selected the top 2000 variable genes. So I'm running the PCA step over here. So it is taking a little bit of time to run PCA. Now PCA has been performed, and it has given, as you can see in the console down below, it has given different principal components I would not go into the detail of theory. I will try to explain it. I've already done in the other video, which already that I've linked. But if time permits, I will upload a short form content explaining the difference of PC. But for short, you can understand that the first principal component will have more variance when compared to second principal component. So basically, the genes that are present in PC1 will have will contribute to more variance in the data as compared to the genes in PC2, and thus the variance goes on decreasing as we choose the PC accordingly. Like PC3 will have less variance than PC2, and PC5 will have more less variance than PC4. So PCA has been performed, and just will be printing now this in the previous part one I've told you the double bracket column will add, the double brackets will add a new column into your object in PBMC. So I'm running this step run, and it has printed the first 5 PCs. The dimension is first 5, and will be having 5 features. Now here, if I want to visualize my Surat object PBMC, yeah. So now we have 3 layers present. We have counts, we have data, and my data is scaled, right? And an object of class is Surat. Okay, now we have these many features, and now we have got 2638 samples. And you see there are 2000 variable features. So all these we have performed. And we have also performed one dimensionality reduction. Okay, and which type of dimensionality reduction has been performed? That is PCA. So everything is stored in the Surat object itself. If you want to visualize the metadata of the Surat object PBMC, so here's the, okay, fine. So you see, these are the things. So the first column is the barcode, and this is the identity that we have given. We have 3 more columns: N count RNA, N feature RNA, and percentage mitochondrial cells that we have already visualized. And here in our code, in the script pane here, so we have all added this PCA here in this one. It corresponds to this layer, right? So one dimensionality reduction calculated as PCA, here it is stored. Now moving on further. So we'll start with the visualization. So this is we'll be visualizing the loading with the help of this uh, code here. So the command wisdom loading in Surat is used to visualize the loading scores of the genes. Okay, and what it does, it takes the first 2 principal components because it has stored most of the variability in it. Okay. The PBMC is obviously the Surat object here, and the DIMS is equal to 1:2. It specified that we are going to take the first 2 principal components, and the method of reduction was PCA. The plot generated by this function will display each gene as a vector. First, let me run this. Right. I maximize this one here. We have the first plot over here corresponds to the genes which has most variance, and the second plot has the genes which has second most variances. Okay, so these are the genes. So likewise, you can visualize the variances. How are you getting this? You are getting this because you have performed principal component analysis. Oh, it is giving you the gene. It will reduce your dimension by giving you only those genes which has maximum variance and thus has maximum effect on your data. Now, as you can see in the plot, some of the genes are on the positive side and have positive loading scores. Positive scores mean that their higher expression is associated with higher values of the principal component. So it is a positive correlation, okay, to the variance. And conversely, the genes on the negative side have negative loading scores, indicating that their higher expression is actually linked to the lower value of variance. Okay, so it shows a negative correlation. That is it. So it's such a simple plot where you can examine what are the effects of your features after the dimensionality reduction. Now we'll be proceeding with generating more plots to visualize this data. So here, after reduction is performed, and we can see a dimensionality plot will be generated. If I run this, you see there are no legends. Okay, so we don't know legends now. And roughly, if you can see, there are three clusters, one here, one this one, and another one is here. So rough three clusters are performed. And if I run this command, right? So further we'll generate a heat. This heat map, how to explain? Okay, so this heat map function creates obviously a heat map to show how the genes are expressed across the first principal component. PC1 is your first principal component. I mean, all those genes that are giving you the maximum variance. And by setting the cells is equal to 500, it uses the data from the 500 cells to create the heat map. The function balance is equal to true, that option. It ensures that the color scale is evenly spread, and it will basically these all are related to visualization only. So making it easier to see both high and low gene expression very clearly. This heat map will help you to understand how the gene expression varies across the different cells based on a first principal component only, and will reveal the important patterns or differences in the data, right? So when we run this, yeah, so I'm running it, right. See, such a beautiful heat map is generated over here, and how to interpret this heat map. The heat map actually helps us to visualize the gene expression distribution across different cells. Basically, you have to look at the colors and you can identify the genes. So this heat map that is generated over here in this analysis represents the gene expression over 500 cells as we have already given. And there are 30 genes, or there are like 30 genes. 30 genes are selected. These are present in the PC1, principal component 1. The colors that you're looking at here, yellow and purple, the yellow one are those which has higher expressions in the cell, and the purple one are those where the expression level is lower, right? So since all these, whether high expression or low expression, they are capturing the major variation in the data. And it shows that these genes are the most significant one in, providing differences of variability in expression across all the cells. The heat map reveals that two distinct group of cells indicating two major cell types. So the yellow zone where the genes like here, sorry, where is it? CST. Okay, so yellow zone, in the full yellow zone, the CST gene, as you can see, then Liz gene, here, Liz gene, and the FCN1 gene. You can search, you can also search with FCN1. Yeah, so this one. So you see, in some cells, these are expressed highly. So in the 500 cells, you see half of the cells have higher expression of these genes and half of the cells have lower expression. So basically, we can see that we have two types of cells when we look at this two blocks, right? So, the yellow zone genes, which I've told now, usually if you go and perform some, literature search, you'll get that these are the marker genes for monocytes or macrophages, right? And the other gene, that is AIF1 and FTL, which are highly expressed. So where is FTL? AIF1 here. AIF1 and FTL, so they are together over here. They are the markers for inflammatory response genes, and they are highly expressed. It is also showing that they are of myeloid lineage. Okay, so they may be monocytes. So, like these insights you will get if we go on for further, literature search. So, moving on with the uh, script, we'll again run this one. Right? Mm, no, this one we have already done. Now, this is same as the previous code, but here not only a single dimension, we are taking the first 15 principal component and we are running this over here. We'll get a more, where we can compare on the basis of different principal components. So you can see I've told you that PC1 is going to give us more variability. You can see so nicely that it has been clustered. But if you look at PC15, you are not getting any different clusters over here. So the variability decreases as the principal component increases, right? So that is clearly visible over here. Next step that we are going to perform is the will determine the dimensionality using an elbow plot. So the next one over here. What do you mean by determining the dimensionality? How many dimensions should we proceed with now? So the elbow plot is a plot which will give you clear indications. So if I run this, it is very easy. So as the points, the curve is decreasing. So here. So till this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we are achieving linearity. So which dimensions we must choose? This elbow plot is telling us. So look for the elbow point. The elbow point is a point where the line starts to flatten. So flattening is still here, right? So here we can tell how many dimensions we are taking. So even here we can see some curves. So the flattening starts with almost 10th principal component. So that is why it is helping us to determine how many what dimensions we can proceed with. So by interpreting this elbow plot, we are deciding that we'll go for first 10 principal components. We'll have a dimensionality of 10. Now we have a reduced dimensional data, and we'll be proceeding further. We'll be performing clustering. So for clustering, we are going to use the function that is find neighbors, and the dimension is first 10 dimensions. And when the clustering has been performed, we will have another plot, and we'll look into the head of the data. So first, let us run this code over here. So computing SNN. So SNN is nothing but a graph. The value of zero point 0.5 is the resolution, and it will be determining the granularity of the clustering. And you can adjust this according to yourself to get more of your clusters. The output shows the cluster identity for the first 5 cells, right? And the graph was SNN, so that is a shared nearest neighbor graph. And here in this, the edges are formed between the data points based on the number of nearest neighbors as they share. And it helps us to reveal the clusters in high dimensional data. It will help in locating the different clusters, and it is often performed only after dimensionality reduction. Running the next, we're looking at the cluster IDs now. So you see here, each cell is depicted with the help of a barcode. So there is no ID given. So first 5 cells ID we have got over here, right? So the ID are all same. PBMC3K because clustering has not been performed. After performing the clustering, fine clusters. After this, we are getting the number of nodes. There are 2638 number of nodes, and this is nothing but the cells, right? So each cell is behaving like a node of the graph, and all the connections are the edges. So 95,905 connections are performed. And now, when we will look at the uh, data over here, so see the identity has changed. What it is telling that the identity is like this cell now belongs to cluster which is numbered as 0. This cell belongs to a cluster which is numbered as 3, and this cell belongs to a cluster which is numbered as 2. And all these clustered are stored as a level. So there are by this what you can find is you have got 9 clusters, each numbered from 0 to 8, right? Moving on, now we have performed PCA. We'll now perform non-linear dimensionality reduction technique, and that is UMAP. This is also dimensionality reduction. So after PCA, we'll be going for a non-linear technique. So here in the Surat object, we'll be running this function that is run UMAP, and again we are taking the first 10 PCA components, right? And then we will be visualizing this with the help of a plot, and the reduction is now UMAP as opposed to PCA that we did earlier. So so same command, but the method of dimensionality reduction is now UMAP. So if I run this one, this code, you see UMAP is been running on the data, and we can also set this. Some commands are here, some comments are here. You can go through them, which will help to label your data or individual clusters. Now, if I plot this, now we are getting a better. So 3 clusters. We are getting 3 clusters, but there are different population within a single cluster. So PCA was not telling us that one. So here you see, even within the 3 clusters, there are subpopulation, and on total, there are 9 clusters that we have got, and each clusters is they are colored differently, right? This is the difference. Now we have got a very important insight on our data. So what we are doing, suppose if we want to do a further analysis, we'll save this as the output. And if I run this, over here, this will be saved in my environment as save RDS, and I'll be putting this in an output folder, right? And I will name it as pbmc underscore tutorial.rds. Now this RDS file you have saved When I call this RDS file later on, what it does, that it has saved all these operations that I've performed. It will contain all these objects in the environment, all these things. So that if tomorrow I want to work again, I would not have to perform this from the very beginning. And I'll just call this pvmc tutorial.rds and I'll apply all the functions or all the operations on this itself. Right? So that is it for today's video, and we will be meeting again in the part 3. So we have now clustered our samples, and what we have found out, that there are 9 clusters in total. The next step would be to annotate this. So all the clusters are not named. We don't know that which type of cells they are, right? So we will be going further by how can we annotate. You have to find the marker genes, and then you have to go and understand that if this particular gene is present, then it will correspond to which particular cell type, and with the help of that we will be annotating our cell types. So that's it for today's video. I hope you really enjoyed this, and we will continue with the part 3. I'll try to upload it soon, and please go through the other materials that I've provided, like the short videos explaining the plots, and you can also go and check the link below in the description box I'll provide for my AI ML classes. In that, basic statistics and graphs are also explained, where you can learn about what is a PCA, what are the principal components, and also other non-linear dimensionality reductions like UMAP or TSNE. Right? So that's it for today. Have a nice day.